The following two solutions from part A are mixed to form a buffer solution. Okay, 20 mils of 1 mole per liter. Look at this. That's like the ammonium ion, right? The weak acid species. And 30 mils of 1 mole per liter CH3NH2, which is like the ammonia molecule. Okay, I'm not saying that it's ammonium ions and NH3s, but in terms of thinking about it, it might be helpful to feel familiar with it. Think of it like something that you know about. Don't write this in your exam. I mean, we can think of it like NH4 pluses and NH3s, okay? In case that CH3 instead of one of the hydrogens in the ammonium frightened you, right? But it's very much like that. So, look at these ones here. A buffer solution contains a weak acid together with its conjugate base, right? Significant comparable concentrations of a weak acid and its conjugate base. So, look at this here, ammonium ions and NH3. If it's a solution that has both those species present, will be a buffer solution. Similarly, and that's a familiar buffer solution. So if we can get that there, this is very much like that. We can have this weak acid, the CH3NH3 1+, as a weak acid, together with its conjugate base CH3NH2. Now, it says here, calculate the pH of the resultant buffer solution. Okay. Now, when we do a buffer solution pH calculation, what we need to do is begin writing the equation for the acid hydrolysis reaction taking place here. This species here, like an ammonium ion, can react with a water molecule. And remember, I've already explained today what a hydrolysis reaction is, an acid-base reaction involving a water molecule. So this one here will give away NH plus to the water, but it's only an equilibrium, not a reaction to completion, because this stuff is a weak acid. So when it gives away the H plus, it will turn into CH3NH2, and our H2O becomes H3O plus. Okay, that's how we have that equilibrium reaction. Now, just when writing our acid dissociation constant expression, rather than having to write Ka equals the products or the reactants like CH3NH2 concentration brackets times H3O plus concentration brackets divided by CH3NH3 1 plus concentration brackets, I can make it neater and simpler to write if I think of the CH3NH2 part like X, and that's what I've done. I put that as X, and then we get H3O plus, and if that's the X, then something that has an H plus more than X will be HX plus, right? So that species we can write as an HX plus H2O liquid in equilibrium with X aqueous plus H3O plus aqueous. What's the X? CH3NH2. But it just means that I can write down the acid dissociation constant expression in a more compact way. Right? It doesn't change the calculation at all. Now, why is that the acid dissociation constant expression? That's the equilibrium constant expression for the dissociation process. The products over reactants. X concentration at equilibrium times H3O plus concentration at equilibrium, those are both dissolved species, divided by the remaining undissociated HX plus concentration in the solution. H2O is a pure liquid, that's the solvent. We do not include that in the Ka expression. Any questions up to that point? No? Then, when you're given a pKa value, P anything means minus log to the base 10 of that anything. pH is minus log to the base 10 of the H plus concentration. So, POH is minus log to the base 10 of the OH minus concentration. So pKa will be minus log to the base 10 of the Ka value. So if you like, I could write it here like this. pKa, just like pH, minus log to the base 10 of the Ka value. So in that case, by our mathematics rules, our Ka value becomes 10 to the power negative of the pKa. 10 to the power negative of the pKa. and they tell us the pKa of this acidic species CH3NH3 1+ is 10.64. So the Ka value of CH3NH3 1+ will be 10 to the minus 10.64. Okay, now look at everything there that's on the board and tell me if you have any question. Our objective is to calculate the pH of the resulting buffer solution when you mix these two solutions together. So there's our Ka expression that we had before, and we know that the Ka value will be 10 to the minus 10.64. And what is going to be the HX plus acidic species concentration after you mix them? And here's a little shortcut that you can use very usefully to get the final concentration. There's 20 mils of the acidic species and 30 mils of the basic species. And they are both at 1 mole per liter concentration. The concentrations are the same, but there's 20 mils that you put of the acid and 30 mils. So in the final solution that you get, the concentration of the acid species will be 2/5, because our 20 mil becomes 50 mils. It will be 2/5 of the 1 molar that you began with. So the acid species HX plus will have 2/5 of 1 molar, which is 0.4 molar. Similarly, the weak base CH3NH2, 1 molar, and we took 30 mils. What's the total final volume? 20 and 30, 50 mils. So after mixing the two solutions, the concentration of the weak base will be 3/5, 30 on 50, 3/5 of the 1 molar, which is 0.6 molar. Okay, so you didn't need to calculate 20 mils converted to liters times moles and then divide by 50. You could have simply taken the ratio of the volume of that acid solution itself to the total volume after mixing. That's what we've done. And the same with the base. Now, this is only a weak acid, and this is where our famous weak acid approximation comes in. This species is only going to dissociate very slightly. And the weak acid approximation that we make with any weak acid, and a corresponding thing, of course, with any weak base, is that the concentration at equilibrium is going to be the same as the initial concentration, because so very, very little of that acid gets dissociated. This equilibrium lies heavily to the left. That is the standard assumption we always make with a weak acid in an equilibrium. Similarly, with a weak base in an equilibrium, we take the weak base concentration at equilibrium as being the same as what it was at the beginning. Okay, so I'll apply that approximation using these numbers when we flip to the next slide. Here, those were the numbers there. Now I'm going to plug values into this Ka expression. There's the Ka value, 10 to the minus 10.64. The base concentration is going to be 0.6 molar. The acid concentration, 0.4 molar. And here's the H3O plus concentration. So I can use this to calculate the H3O plus concentration and then get the pH. Right? That's what's going to happen now. That means the H3O plus concentration will be 0.4 on 0.6 times 10 to the minus 10.64, which gives us 1.527 times 10 to the minus 11. That's the H3O plus concentration. How do we get pH from that? The pH is minus log to the base 10 of the H3O plus concentration, this part in the red now. And that's minus log to the base 10 of this value here, circled in purple, which is where I get that number from. 1.527 times 10 to the minus 11. And that gives a pH of 10.8. Okay, there. So make sure you've understood that. Don't just write it down. I'm more concerned about the understanding. Why? Because we're studying a chemistry course, not a secretarial course. Then we'll look at the part 2 of this. See part 2. Explain the effect on the solution formed in 1 when a small amount of acid is added. The effect on the solution formed in 1 when a small amount of acid is added. Small amount is the important word, because buffer solutions cannot, shall we say, resist pH changes to unlimited additions of acids or base, strong acid or base. But if you add a small amount of it, the buffering action minimizes the pH change. Now what will happen when you add H3O pluses here? you'd write this equation in explaining this, because that's the buffer, the equilibrium involved in this buffer. So we are adding a small amount of an acid. Adding a small amount of an acid will cause most of the added H3O plus to get used up. As a result, there won't be any significant change in the pH of this buffer system. Now, just telling you something else along the way. Usually when we make buffer solutions, if we think that there's just as likely the possibility of acid being added to it or base being added to it, you'll have close to equal concentrations of the weak acid and its conjugate base. So the buffering action is a maximum when you have equal concentrations of the weak acid and its conjugate base, okay? But this one here, because it was more on the acid side, there was more base, it'll be better at resisting pH changes when acid is added, because there's more base there, okay? So other points worth noting or something, you can write it down. Usually we have very similar concentrations of weak acid and conjugate base in a buffer. Then the buffer will be just as effective in resisting pH changes to the addition of an acid or a base. In this particular case, the concentration of the base is higher, so it will be better at buffering against the addition of an acid compared to the addition of a base. Okay, why is this? Because there's more base, and what does the base react with? With the acid. So it's better at resisting changes to the addition of acid than to the addition of a base.